Greetings everyone, this is Professor Roman. Let's continue the lecture series on linear algebra. We finally come to the point where we can discuss and prove two cornerstone theorems in linear algebra, Schur's theorem and the spectral theorem. It has been said by some very knowledgeable people that Schur's theorem is probably the single most important result in all of matrix theory. So that's a pretty impressive statement. In this chapter and in this forthcoming discussion, the field F will always refer to either the real field or the complex field. Also, all vector spaces will be assumed to be finite dimensional. As we've discussed, one of the main goals of linear algebra is to find relatively simple matrix representations for any linear operator, tau, on a finite dimensional vector space V. But since matrices are generally easier to work with than linear operators, it's often simpler to pass to any matrix representation, call it tau sub b, script b, b is an ordered basis of tau, and then search for a relatively simple matrix B that is similar to the matrix representation we did find. That way we can work exclusively in the realm of matrices. Find any matrix representation and then look in its similarity class for a relatively simple matrix. Then that matrix will represent the operator as well, because it's similar to the matrix representation we started with. Just to be perfectly clear, because I want to avoid any possible confusion, you will see if you look in many books on linear algebra, perhaps most, that some theorems will be stated in matrix versions and in operator versions separately. That's really not necessary. It might help clarify certain things, but it's not really necessary. Let me illustrate. Here are two versions of Schur's theorem. We discussed unitary similarity briefly before. We'll do it again very soon, so don't worry about that term right now. The matrix version of Schur's theorem says every complex matrix is unitarily similar to an upper triangular matrix. The operator version says every finite dimensional complex linear operator has an upper triangular matrix representation under an orthonormal basis. Now, the orthonormal basis part connects with the unitary similarity. But the point is, these two theorems are equivalent. They say the same thing. And the easiest way to see that is to note that both of these statements are equivalent to the statement that every unitary similarity class contains an upper triangular matrix. That tells us that every matrix is unitarily similar to an upper triangular matrix, and at the same time it tells us that every linear operator can be represented by an upper triangular matrix. So these two theorems are just different ways of saying every unitary similarity class contains an upper triangular matrix. So that could also have been stated as Schur's theorem. Let's take a look then at unitary similarity. This might not be a bad time, however, to review the discussion of change of orthonormal basis matrices that took place in Chapter 5, so some time ago in the lectures, in particular culminating in Theorems 5.67, 5.68. So if you're a little uncomfortable with change of orthonormal basis matrices, I would suggest you go back and review that. But let's forge ahead now. Since orthonormal bases have a major advantage over ordinary bases, as we've seen, it's much easier to represent arbitrary vectors as linear combinations of members of an orthonormal basis than it is an ordinary basis. There is a significant advantage to finding matrix representations of linear operators with respect to orthonormal bases. So we need an inner product space for that. And for this, we need a special type of matrix similarity, and that's the unitary similarity. Two complex matrices are unitarily similar if they bear this relationship where U is unitary. I gave you this definition a while ago. I don't remember when, so this is not new. Also, two real matrices, A and B, are orthogonally similar if they bear this relationship where O is a real orthogonal matrix. And remember, that means that O is a real matrix that has orthonormal columns and therefore rows. And we had a discussion about the fact that this is really somewhat misleading terminology. It's not enough for the columns to be orthogonal, they have to be orthonormal. I'm going to use the notations here that you won't see elsewhere, I don't think, for unitary similarity and orthogonal similarity. I just put subscript U and subscript O. We could do without it, but at times it'll be convenient, so I'm including it. I'm sure you remember from way back in Chapter 2 the discussion to the effect that two matrices represent the same linear operators if and only if they're similar. And we had a change of matrix representation formula. There's a complete analog in the setting of unitary similarity. Here's the picture. In this case, we have the n by n matrices over F. In Chapter 2, we partitioned this into similarity classes. Now we're going to partition it into unitary similarity classes. So you need to double check that unitary similarity is an equivalence relation, which it is. These equivalence classes in general will be smaller than the ordinary similarity classes because if two matrices are unitarily similar, they're also similar, but the converse is not necessarily true, as we will see. If we start with a linear operator tau and we scan through all the orthonormal ordered bases, what will happen is we will fill one unitary similarity class. So it works the same way as it did before for ordinary similarity and ordinary similarity classes. This is a statement of the theorem that corresponds to Theorem 2.72. Let V be an n-dimensional inner product space and let tau be a linear operator on V. The matrices that represent tau under various orthonormal bases form a single unitary similarity class. And these are the specifics. any two matrix representations of tau under orthonormal bases, B and C, are unitarily similar. This is the similarity. This, because B and C are orthonormal bases, the matrix MCB is unitary. And so its inverse is equal to its adjoint. And so the ordinary change of matrix representation formula becomes this, and these two matrices, and this matrix is unitary, and so this is a unitary similarity. Also, it's worth noting separately that, excuse me, when the base field is real, all these matrices are real. Everything happens in the real universe. Conversely, if we have one matrix representation of tau, and B here should be an orthonormal basis, I don't think I made that clear, so I better do that. U is unitary. Then the ordered orthonormal basis C, that is uniquely determined by this equation, has this property telling us that B is also a matrix representation for tau, but under the orthonormal ordered basis C. So this is the specific details on this statement up here. And as I promised, let's look at the difference between ordinary similarity and unitary similarity. They are not the same. Two matrices can be similar, but not unitarily similar. Here's one way that can happen. If a complex matrix A is unitarily similar to a self-adjoint matrix, so here's A, here's B, B is self-adjoint, then A must also be self-adjoint. I didn't prove this, I left it for you. Example, then, A is this 2 by 2 complex matrix. Here are the eigenvalues and the eigenspaces. And so the standard basis vector E1 and the vector V1 together form a basis, an eigenbasis, in fact, for the matrix A, or operator A. And so A is similar to this diagonal matrix. But this matrix is self-adjoint, and A is not self-adjoint. You take the conjugate transpose, you don't get A back. Conjugate transpose here of B is equal to B. So these two matrices, A and B, are similar, but they cannot be unitarily similar. Why orthonormal bases? We already know one reason they're easier to work with in terms of finding the coordinate matrices for vectors. But I want to drive this point home. I want to point out something that I have not seen pointed out in general in the courses, in textbooks on linear algebra. In searching for a relatively simple matrix representation for a linear operator, it's important to realize that from a practical perspective, there are really two issues that need addressing. And we can see that by looking at how a matrix representation is actually used to compute the image of a vector. That's what it's all about. This is the formula. Tau v sub b, the b-coordinate matrix of tau v, is the matrix representation of tau times the b-coordinate matrix of v. So to use this formula to compute this quantity, which is equivalent to computing tau of v, we've got to do two things. First, we have to find the coordinate matrix of v with respect to b, and then we have to multiply by the matrix representation of tau. So the choice of basis b needs to be made with two objectives in mind: finding a nice matrix representation so we can apply it easily, and we might want to apply it 1,000 times. In other words, take this matrix and raise it to the 1,000th power. So a diagonal matrix would be really nice here, if we can find one. But also, we need to be able to compute coordinate matrices of vectors relatively efficiently. We're speaking now in practical terms. In theory, it doesn't matter. But in practice, there are two computations going on here. The computation of the coordinate matrices of vectors, and then the multiplication by the matrix representation. Now, once we find the matrix representation, that's a static issue. That doesn't change. But we may want to cycle through many vectors to compute many images. And so the computing of coordinate vectors or coordinate matrices of vectors becomes more important from the practical standpoint. So this is why finding an orthonormal basis matrix representation is more desirable. Okay. Now we can get down to work here. Finding relatively simple matrix representations for any linear operator tau is much easier when the minimal polynomial of tau, or equivalently its characteristic polynomial, splits over the base field. So we're going to consider that case first. Of course, if the base field is the complex field, all non-constant polynomials split, so we don't have to worry. But when the base field is the real field, some non-constant polynomials will split and some will not. So it becomes an issue. It is traditional in the books I've seen over the years, and I've been, let's see, when did I first teach linear algebra? Sometime in the early to mid 1970s. And so when I say it seems, in my experience, I've had considerable experience over the years, this material generally gets split into dealing with the complex base field and the real base field, two different issues. The complex case is, as I mentioned before, simpler than the real case because all the polynomials, non-constant polynomials, split. The real case is more complicated because sometimes the minimal polynomial will split and sometimes it won't. I think that's a little bit of an artificial separation into real and complex. So I've chosen a slightly different path, and that is to split the discussion into two cases. One is where the minimal polynomial splits, and the other is where it doesn't. That is really the issue. The issue is not whether the base field is real or complex. The issue is whether polynomials split or do not split, relevant polynomials. Okay, so that's why you will see in this course a little bit different way of splitting up the cases. And also, I've noticed in some of the recent linear algebra books that I've considered using for courses that the real case isn't even covered, or covered very superficially. And the complex case is covered carefully. I think the reason for that is that life is more complex in the real case. But one thing, and time is a consideration in ordinary courses, so I can understand why it has to be done that way. Fortunately, we don't have that restriction in these lectures. But the point is, to me anyway, that the techniques are exactly the same in both cases. It's just that the techniques don't work quite as well, you might say, in the real case, or in the case where the minimal polynomial does not split. And the reason, of course, is that you have to deal with irreducible quadratic factors of the minimal polynomial. But the techniques are the same. It's just that the results are a little bit more complex in the real case. And you will see all that as we go through this, because I left nothing out in this course. We're going to cover everything. So, finding, so our first case, our first consideration is going to be for linear operators whose minimal polynomials split, or equivalently whose characteristic polynomials split. Finding a relatively simple matrix that is unitarily similar to a given matrix. So we're, as I said before, working in the universe of matrices. This can be done by repeated applications of a process that is sometimes called deflation. You won't see that term very often, but it is in the literature. It's in a very important book on matrix theory by Horn and Johnson, for example. And it's a terrific term. It should be used much more often than it is. Deflation is really pretty simple. It uses an irreducible factor of the minimal polynomial of the matrix to produce an invariant subspace. Invariant subspaces are the key to finding simple matrix representations. In fact, reductions are really what we're after. And that's why we have to use repeated applications of deflation. Each application produces a single invariant subspace. Now, since we're assuming for the time being that the minimal polynomial of our matrix splits, all the irreducible factors are linear. So here's how deflation works. If x minus lambda 1 is a linear factor of the minimal polynomial of matrix A, that means lambda 1 is an eigenvalue. It's a root of the minimal polynomial. And if this pair, lambda 1, u1, is an eigenpair for A, and specifically we normalize the eigenvector so that u1 is a unit eigenvector, then the subspace spanned by u1 is A invariant. This is an eigenvector. And we can extend this one element orthonormal set, that's why I wanted a unit eigenvector, to an orthonormal, ordered orthonormal basis for Fn. The matrix representation of A with respect to this basis then tells us that A is unitarily similar to U star AU. And that is the matrix representation of A with respect to this ordered orthonormal basis. And it looks like this. We have lambda 1 in the upper left corner. This is a block matrix. We don't know what's up here. These are all 0. And we don't know what's down here, but I call it R because we're going to need to refer to it. I think we did this before. Okay. And U, the similarity matrix here, is just the matrix whose columns are the orthonormal vectors. Because we're dealing with vectors in Fn, so these are legitimate columns. This matrix is unitary. And if we started with a real matrix, then U is real, everything's real. So U is real orthogonal. Well, the simplicity of this first column is a really good start towards finding a simple matrix that is unitarily similar to the original matrix A. I'm going to call this deflation a linear deflation. And that's simply because we used a linear factor of the minimal polynomial to perform the deflation. So the process of producing, finding this matrix is starting with the matrix A, finding this matrix that's unitarily similar to A, but begins to have a nice form, is called the linear deflation. Schur's theorem results from and also, forgot something important, this matrix R we will call the residual matrix for the deflation. It's what's left over, so to speak. Schur's theorem results from repeatedly applying linear deflations to the residual submatrices. And here it is in picture form. A is unitarily similar. This is the first deflation. I called it R1 here now. Maybe I should have done that before. We take R1. That's a matrix of whatever size. And, well, this is 1 by 1 here, so this has size 1 less. This was, if A was n by n, R1 is n minus 1 by n minus 1. We just take that as a standalone matrix and we apply another deflation. So this part that's shaded here is the deflation of R1. And then we deflate, and so we get what matrix that looks like this. We deflate another time. We deflate R2. We get a new residual matrix, R3, a new eigenvalue. These eigenvalues, by the way, some could be equal. But this is the process that we undertake, and eventually this part in the shaded box has size 1 by 1. and we can stop. And what do we have? An upper triangular matrix. Okay. So here are the details, basically saying what I just said. Our first deflation uses an ordered orthonormal basis, a linear factor, ordered orthonormal basis. I didn't do that quite right. I better fix this. And we get this first deflation. Now, there is one point here that we have to pay attention to. If we take this matrix here, the first residual matrix, it's a submatrix of the whole matrix A. Its minimal polynomial divides the minimal polynomial of A. We had a theorem to the effect that when you have block upper triangular matrix, the minimal polynomial of the whole matrix is the least common multiple of the minimal polynomials of the blocks divides the minimal polynomial of the whole matrix. So the minimal polynomial of R1 also splits. That's the important point. Okay. If we didn't know that this minimal polynomial of R1 was a factor of the minimal polynomial of A, we don't know whether this minimal polynomial splits or not, and we could get stuck. So we don't have that problem. Also, wanting to be as neat and tidy as possible, after we deflate using this linear factor of the original, the minimal polynomial of the entire matrix A, we want to do another deflation now of R1, whose minimal polynomial divides MA. To be as neat and tidy as possible, we'll first check to see if this same linear factor is also a linear factor of the minimal polynomial of R1. And we will use it, if it's true, we'll use it for the next deflation. That way, and that way we can keep all the lambda 1s together along the diagonal. This is not critical, but it's neat and it's tidy. We also have to address what might be a concern, should be a concern, frankly. We deflate this submatrix. How do we stick it back into this matrix? I just drew a picture here, but why is this? Remember, this is a similarity. So how do I know these two are similar? And I want them to be unitarily similar as well. Well, we can combine the first and second deflation. The first deflation is a deflation of A. The second deflation is a deflation of the residual submatrix that we got from the first deflation. How do we fit those together? Well, it looks like this. We form the unitary matrices that do these two deflations have different sizes. U1 here has the same size as A, U2 has the same size as R1, so it's smaller by one row and one column. So we can't just multiply U1 and U2 together. They're not compatible. We have to upgrade U2 by sticking a 1 up here, and then this will be a row of zeros and this will be a column of zeros. This is still unitary because U2 is unitary. This is unitary, so this whole mess here in the square brackets is still unitary. Here, this is the adjoint of this. So this is a unitary similarity here. Now, U1 star A U1 is this first deflation, so it looks like that, and we have these two matrices on either side. Block matrix multiplication takes us to here, which is what we wanted, which is what I showed in the picture. Lambda 1, lambda 2, R2, asterisk 0. Lambda 1, lambda 2, R2, asterisk 0. So the picture is accurate. I didn't draw the picture till after I did this computation. So it all fits together neatly. And we have a unitary similarity of A and this matrix, which is another step towards a very nice form, towards upper triangular form. Now it should be relatively clear that we can do R2, we can deflate R2, and continue the process of deflation until we get a 1 by 1 residual matrix, and then we stop. Also, we should point out again that if the base field is real, all this takes place in the real universe. All the matrices are real. We have proven Schur's theorem in the case where the minimal polynomial splits. So, matrix version, equivalent operator version. Any matrix A whose minimal polynomial splits over F is unitarily similar to an upper triangular matrix of this form. I shaded these boxes just to emphasize that lambda 1 was the first eigenvalue we found. We grouped all of the lambda 1s that appear in this matrix together by that neat and tidy business we talked about earlier. So we've got a block here, a diagonal block, an upper triangular block, where all these are lambda 1, then come all the lambda 2s, and so on. And this is the operator version, which says that any linear operator on V, any finite dimensional linear operator whose minimal polynomial splits has an upper triangular matrix representation via an orthonormal basis. Okay. I guess maybe I should have said V is an inner product space. It has to be. That's what we're discussing. You can't have an orthonormal basis unless there's an inner product. So that is Schur's theorem. Again, one of the, perhaps the single most important theorem in all of matrix theory. This form of matrix that we get by these deflations, we will refer to as a Schur form of the original matrix A. So this is in Schur form. I think that's a reasonably common term, but I'm not sure. S-U-R-E. The Schur form of a matrix, however, is by no means unique. There's considerable free choice in the deflation process. For example, we have freedom of choice for the first linear factor, which will change the very first entry. Even if we stick with a single linear factor, a single eigenvalue for implementing this process, we have to extend a single unit vector to an orthonormal basis. That can be done in a lot of different ways, so we get different residual matrices. So there's all sorts of ways in which the process can be implemented and will result in different matrices. And just to be absolutely convincing, here's an example. Consider this matrix here. Here is an eigenpair, eigenvalue 1, and a nasty-looking eigenvector. If we want to deflate A using this eigenpair, then we would take this vector and we would extend it to an orthonormal basis for R2. So here's U1 and here's one possibility. Easy enough to see that these are orthogonal. And the value of A on U2 is given by this formula. So the deflation is this matrix here. It's the matrix representation of A under this orthonormal basis. So this is a Schur form of the matrix A. But I could have made a simple change in the orthonormal basis. Instead of U1, U2, use U1, negative U2. Still a unit vector, still orthogonal to U1. Deflation process would give this. So simple change, but still different Schur form.